start recording here. Today is, it's Valentine's. And we're going to talk about rat love. Well, just rat sex, actually. We're not so sure about the love part. Heck, they eat their own babies sometimes. But, yeah, what kind of love is that? Seriously. So, exponential curve. What does it look like? And I like doing exponential curves with sound effects, so I'd like you to all join me in standing up. Nah. Okay, so, no, and not funny. So anyway, this is an exponential curve. At every point on this line, the bigger it gets, the faster it grows. The rate of change increases. Because it's like a doubling problem. Every moment it doubles. Well, turns out we can model, and you know, models are not just like little glued together airplanes and stuff. We can have a mathematical model, we can have a graph that represents something, and that's a model. So we can talk about exponential growth of a population. And the exponential growth model says, well, if we have a population that just keeps, for instance, doubling, it grows really, really rapidly, and very quickly, after just a few generations, you have an enormous population. Does anybody have barn cats at home? Okay. Barn cats are fantastic to illustrate this kind of growth. So are mice. Does anybody raise mice? Okay, we'll talk about mice in a second. So here's the thing. We're going to talk about two different models for growth. And in each of the models that we talk about, look for the word assumes. Okay? There is an assumption that underlies each model of growth. And for this exponential growth model, the assumption is that birth and death rates don't change. Doesn't matter how many individuals you get, they keep reproducing at the same rate, and they never die at a higher rate. We call it J-curve growth very often because it looks like a J. Some people call it a hockey stick. And in this model, the larger the population gets, the faster it grows. So, years ago in college, I had a friend who had some pet mice. Anybody here had pet mice? No? Really? I had mice in my classroom for a while, and then I think somebody poisoned them, and they both died within a day of one another. It was really, I've never had an animal in my room since. So, Sally had, I think she started off with 3 mice. Yeah. And she had 2 tanks, and you have to separate the males and the females. Why? To keep your population constant. Because if you put them together, oh, hey, it's Valentine's Day, mouse love. Or at least mouse sex. And then baby mice. So she thought she had 2 females and a male. And she had a tank with the 2 females, and she had a tank with the male. But she was wrong. She had 2 males and a female. And guess who was in a tank together? A boy and a girl. And so I think their gestation period's like 16 days or something ridiculous like that. So she had a litter of baby mice. Oh, crud. Okay, well now it's really easy to tell who the girl is. So she got the male out, because what will the males do? Eat the babies. Ew, but it happens. So she got the male out. She, scrounged another tank from someplace. Okay, so now she's got the mama and the 7 babies, and so here, let's graph this. Basically, what mouse growth looks like is that. And she ended up with 200 mice. It was bad. It was terrible. She ended up selling them to a pet store for snake food. She couldn't get rid of them. I mean, it was insane. And once you get to a certain point, I mean, you're trying to, sex identify all these mice, and their genitals are teeny tiny. I don't even know how to sex a mouse. I know how to tell a rabbit, I don't know how to tell a mouse. And so you're separating them wrong, and then you've got a tank with 4 individuals in it, and it turns out one of them's a male. Ha ha! Those 3 girls are now pregnant. And then you've got another tank with, what you think is 5 males, and it turns out 2 of them are females. Ha ha! They're both pregnant. Oh my gosh. That, my friends, is exponential growth. The bigger that population gets, the faster it grows. So she started out with 10, and it took 4 weeks for that population, or started off with 3. It took 4 weeks for that population to go from 3 to 10. In another 7 weeks, it went from 10 to 40. In another 4 weeks, it went from 40 to near 100. The bigger the population gets, the faster it keeps growing. So that is exponential growth. Now, does this happen in nature? It's crazy. No. This doesn't usually happen in nature. Sally's house was not nature by a long shot. She kept providing more food and more cages, and, God, it was a nightmare. And it was stinky, too. Had this been happening in nature, what you typically would see is that you can have that population spike like that, but it's followed by a crash. So I would invite you all once more, after you finish writing, to stand up, because we're going to put the second part of the sound effects and the dance moves in. In general, what happens when we see this situation in nature is you have a short time, and then suddenly individuals start dying because they run out of food, they run out of space. Basically, their own waste piles up. I mean, if you can imagine the amount of waste that, oh God, like 250 mice generate. She was changing shavings. Oh, it was insane. It was horrible. I think she got rid of all the mice after that for a little while. A little bit burned out on mice. But in the wild, had she not been there to change shavings, to put in more food, to add more tanks to the situation, they would have just started dying. There wouldn't have been enough food for them. There wouldn't have been enough space. They would have started eating one another. That's what happens. So let's do a sound effect. So generally, anytime we've got whoop, we have boom. Oh, there's one of my little bug friends, speaking of populations. The other place we see this is bacteria in a lab dish. So I used to do water sample cultures when I worked as a watershed coordinator. And we'd sample creek water, put it in a little petri dish, and in some cases, that dish would be completely full. And if you left it in the incubator, the bacteria would just cover the surface of the plate. And the whole entire thing would be a bacterial colony. Well, that can only go on for about so long, because then guess what happens? Whoop, boom. It crashes. Their waste spilled up. They're basically not eating anything. They run out of food. Waste pile up. The population crashes, and they all die. On that cheerful note, let's look at what really does happen in nature more. So this is called the logistic growth model. And it's also sometimes called S-curve growth, because what it says is a population can grow for about so long, and then the growth rate starts to change. And notice that the curve of that line starts to taper off, and then it kind of flattens out. And remember I said look for the word assumptions? The logistic growth model assumes that as you get a bigger population, births slow down and deaths increase a little bit. And so the growth rate tapers off, so you don't have that crazy growth. And what the logistical growth model assumes is that you get to some point where it's this stable population, and it just fluctuates around this stable point, and that would be what's called your carrying capacity. And carrying capacity is how many individuals can actually live in that environment over the long term. So with the resources that are available, if you've got a functioning ecosystem with all the pieces working together, how many individuals can the system support? 1 to 2 to 3 to 4 to 5 to 6 to 7 to 8 to 9 to 10 to 11 to 12 to 13 to 14 to 15 to 16 to 17 to 18 to 19 to 20 to 21 to 22 to 23 to 24 to 25 to 26 to 27 to 28 to 29 to 30 to 31 to 32 to 33 to 34 to 35 to 36 to 37 to 38 to 39 to 40 to 41 to 42 to 43 to 44 to 45 to 46 to 47 to 48 to 49 to 50 to 51 to 52 to 53 to 54 to 55 to 56 to 57 to 58 to 59 to 60 to 61 to 62 to 63 to 64 to 65 to 66 to 67 to 68 to 69 to 70 to 71 to 72 to 73 to 74 to 75 to 76 to 77 to 78 to 79 to 80 to 81 to 82 to 83 to 84 to 85 to 86 to 87 to 88 to 89 to 90 to You know, things like Sally's mice or bacteria in a petri dish aren't fully functioning ecosystems. There's nothing producing food in that mouse tank. Sally is putting food into the mouse tank. You know, in a petri dish, you have food in the form of the jelly plate that's on the bottom of it, but there's nothing that's producing new food. So it's not really a perfect model. And if we look at most populations in nature, we do see something that approximates this. It's not perfect, but we get up to this carrying capacity, and then the population sort of dips and rises around the carrying capacity. That's what we expect to see. The things that we define in a logistic growth model. Limiting factors are what limit the carrying capacity. So it's what limits the growth of the population, it's what limits the size of the population. And we assume that carrying capacity does not change. This is an assumption that we make. And this is pretty common in wildlife populations. It's common in populations of plants. We see it a lot of places. So of course you know there are sound effects and dance moves coming. We have dance moves in chemistry too. It's okay. It's not just you guys.